Welcome to the next lecture, lecture 29. Here we will be discussing on memory hierarchy design. Furthermore, let us take this example. Here consider a two-level memory hierarchy consisting of a cache memory M1 and main memory M2. Earlier we said that we have two levels of memory, M1 and M2. So generally the level which is closest to the processor, we call it cache memory, and then the next level of memory can be different levels of cache memory we can have, or we can also have a main memory. So the picture here what we are showing, which says it's a two-level memory hierarchy, M1 and M2. M1 is the cache memory and M2 is the main memory. Suppose that cache is 6 times faster than main memory and the cache can be used 90% of the time. So these are the two things which are given. The cache is 6 times faster than main memory and it can be used 90% of the time. How much speed up do we gain by using cache? So here R will be 6 and H will be 0.90. So we simply put into this formula 1 by H by R. H is 0.90 divided by 6 plus 1 minus 0.90. So we are getting 4. So we are getting a speed up of 4 if this particular thing is there where the cache can be used 90% of the time, and that 90% of the time where cache is used, it is 6 times faster. So it is pretty similar to what we discussed way back in Amdahl's law. Now can I take another example where we consider two-level memory hierarchy with separate instruction and data caches in level 1 and main memory in level 2. So here the scenario is we have I cache, instruction cache, we have D cache, data cache. So the instructions are brought and kept in instruction cache, the data are brought and kept in data cache. So the advantage would be like if you want to access data and instruction simultaneously, you can go for it, you can do that. The following parameters are given. So see what are the parameters that are given. The clock cycle time is 2 nanoseconds. This is the clock cycle time. The miss penalty is 15 clock cycles. Total clock cycles is 15 for both read and write. We will be seeing in detail what is read and write, but for the time being let us understand that for miss penalty total 15 clock cycles are required, out of which it says that 1% of instructions are not found in I cache and 8% of data references are not found in D cache. 20% of the total memory access are for data, and cache access time including hit detection is 1 clock cycle. So these are the following information that is provided, and we will be seeing how we can find out the average access time. So let us see. Out of total memory access, 80% are for instruction and 20% for data. Out of this 80% of instruction cache can be used 0.99% and miss rate is 0.01, where the data is not found in I cache. Similarly, for data access, 8% there is miss, so 0.92 will be hit. What is T miss? We have already seen earlier that T miss is the time that is a miss penalty that is used to transfer a block from main memory to your M1 level of cache, and then the access time of the cache. This will be taken into consideration. So, for that Tmiss is 1 plus 15. So, 15, if you go back to one slide, the miss penalty is 15 clock cycle and cache access time is 1 clock cycle. So, the miss penalty will be bringing that block plus including this, because you have to transfer the data. So, total Tmiss time will be 1 plus 15, that is 16 cycles. So, average number of cycles per access will be how much? Miss penalty is this. So, 0.80, that is 80% of the time we are accessing instruction, and when there is a hit, it will be accessed from cache, that is M1. If there is a miss, that is 0.01, this is the miss penalty, that is 16, plus 0.20, that is 20% of the instructions are data accesses. Here 0.92 will be hit and 0.08 into miss penalty will be miss. So, if we calculate this, we are getting this much. This is the average number of cycles per access. So, per access we will be requiring 1.36 average cycles. Now, what is the clock cycle time? It is 2 nanosecond. So, if the clock cycle time is 2 nanosecond, so the average access time will be this average number of cycles per access multiplied by 2 nanoseconds. So, we are getting 2.72 nanosecond. So, in this example, we have seen that what happens when there is a miss, what happens when there is a data is found in cache, and now the cache is divided into two different levels. One is I cache, which is instruction cache, another is D cache. So, when you have two different cache, the calculation will be made in this particular fashion. Let us see the performance calculation for multi-level hierarchy. So, generally we have multi-level hierarchy rather than from two-level hierarchy. In two-level hierarchy, we have only two levels, that is M1 and M2. Okay. To show an example, this is perfect, but in reality we have multiple levels. So, in multiple levels, whatever we have done for two levels, it can be extended to multi-levels, and in multi-levels what we have? We have many levels of memory. So, if you see this particular diagram, which is considered as the most practical memory system that obviously use more than two levels of hierarchy, after CPU the first level is M1, which is L1 cache, the next level is M2, which is using L2 cache, the next level is M3, which is using L3 cache, then M4 is the main memory, and finally M5 is the magnetic disk. So, how do we calculate? So, as we can see that the access time of this will be much faster, then this, then this, then this, and data from main memory is brought through L3 to L2 and then to L1, and when it is in L1, because of locality of reference, we will get the data whenever CPU is asking for a data, it will get in L1. But initially remember, there will be a miss because there will be no data in the cache initially. Whenever the data is loaded in main memory, whenever it is required, it has to be first brought from main memory through different levels to L1 cache, and finally it goes to CPU. So, for the first time there will be miss always, but for consecutive time there will be obviously hit because of locality of reference. So, M1 to M4 is managed by hardware This is very important. So, the cache memory module, the main memory, these are entirely handled by hardware, but M4 to M5 is handled by operating system. Now, let us see this. We have one more level, 3 level of memory hierarchy, where TL1 is the access time of M1, TL2 is access time of M2, HL1 is the hit ratio of M1. That means the percentage time the data or instruction is found in L1 cache. HL2 is the percentage time the data or instruction is found in L2 cache, which is not found in L1 cache, but found in L2 cache. So, hit ratio of M2 with respect to the residual access that try to access M2. Consider a 3 level hierarchy. This is a 3 level hierarchy, consists of L1 cache, L2 cache and main memory. Whenever there is a miss in L1, we go to L2. Obviously, if we do not find the data or instruction in L1 cache, we move to L2 cache. What will be the average access time now? Earlier we have done average access time taking into consideration this particular, the CPU first access L1 cache. So, TA was equal to hit ratio for M1 into access time of L1 plus miss rate, that is 1 minus H multiplied by miss, T miss, that is either it is TB plus TA1. Now, what is the average access time of this particular scenario? In this particular scenario, the average access time is considered as hit of L1 into access time of L1 plus 1 minus H L1 into access time of T L2, but there is a hit in H L2. So, I will just put forward it here. So, now we are saying this is processor, this is L1, this is L2 and this is your main memory. So, what will be the TA, average access time? The average access time, this hit ratio of this is, let us say H1, this is H2. This is TA1, this is TA2 and this can be TA3. So, if this is so, taking simple thing into consideration, H1, so firstly we will consider that we got the data in L1 cache. So, hit ratio into TA1 plus we need to consider that it is not found in L1 cache, but found in L2 cache. In that scenario, what we have to do? It is not found in L1 cache, so 1 minus H1, but it is found in L2 cache. So, it will be TA2. And now, it is not found in L1 cache, not found in L2 cache, but found in main memory. So, 1 minus H1, 1 minus H2, this is TA3 or equivalent to this can be T miss. This is how we find out. We found in here, we say it has found here. We have not found it here, but we got it here, we say this. Now, we say that we have not found it here nor here, but we have found it here. So, in that case 1 minus H1, 1 minus H2 and this TA miss will be taken into consideration. So, this equation is the same, H into H L1 into T of L1 plus 1 minus H L1 into H of L2 into TL2 plus 1 minus L1 into 1 minus L2 into T miss of 2. So, here T miss of 2 is the miss penalty when the requested data is found neither in M1 nor in M2. So, this is the miss penalty now, where we say that the data is neither found here nor found here. So, now you have to bring a block of data from here to here, then from here to here and finally from here to there. So, this is the equation for 3 level of memory hierarchy. So, what is the implication of the memory hierarchy to the CPU? So, we can say that the processors designed without memory hierarchy are simple because all memory access takes same amount of time. Misses in a memory hierarchy implies variable memory access time as seen by the CPU. Why? Because access time of L1 cache is different from access time of L2 cache, and it is different from different as compared to main memory. So, this time of different cache, different access time is different for different memory hierarchy, different levels of the memory hierarchy. Some mechanism is required to determine whether or not the requested information is present in top level of memory hierarchy. So, how can we check this? That means it is saying that if there is some mechanism through which we know that the requested word is present in the top level memory hierarchy. Check happens on every memory access and affects the hit time, and implemented in hardware to provide acceptable performance. That means what we are trying to say. So, what we are doing? We are first checking into top level, that is your L1 cache. So, is there any mechanism that we in advance know that this particular word is there or not, or the checking, can it be made little fast, that when we are checking for this this particular word is present or not, can this check be made little faster, that hit time can be made it little faster. So, there are some kind of things that can be done. Check happens on every memory access, and that is why it affects the hit time. So, if you can have some kind of hardware implementation where this, for this matching, it can be performed in hardware, then it will be good. Some mechanism is required to transfer blocks between consecutive levels. As we know that if there is a miss in both L1 and L2 level, you have to bring a block from main memory to L2 level and then from L2 to L1 level. So, whenever there is a miss in some level, you have to transfer the block. So, you have to do that to get the data. So, if the block transfer require tens of clock cycles like cache or main memory, it is controlled by hardware. But if the block transfer requires 1000 clock cycles like in main memory, secondary memory, etc., it can be controlled by software. Basically, the secondary memory part is controlled by software through a different technique. So, at this point of time, few question arises. One is block placement. So, now let us say we have different levels of memory. So, again we have processor, we have L1 cache, we have L2 cache, and we have main memory. You have main memory. Now, it has got some blocks. It is smaller as well. It has got some blocks. but the number of blocks will be more as compared to this, and this will also have some blocks. Now the point is where we will make the placement of block. So from here, where we will bring the block from here and place it here. So that needs to be understood. Next is block identification. What is block identification? How is a block found if present in a upper level? So we must be matching something. When the CPU generates a logical address and it says that okay, this is the logical address, I am looking for this particular word, then something must be matched to know that how is that block found, is present in the upper level or not. So block identification is also important. Similarly, block replacement. Which block is to be replaced on a miss? What do you mean by that? Now you see, in this particular diagram, here we have more number of blocks, here we have less number of blocks, and we are saying that every time the processor accesses the L1 cache, it will be the fastest. So all the programs or data are brought into L1 cache and then it is accessed to the then it is given to the processor. Now the size of this is small, so at a time limited amount of blocks can be present here. So if you want to run, your program can be much larger, which requires more number of blocks. So in that case, what you have to do? You have to replace some of the existing blocks from here and bring a new block. So for that, some block replacement strategies must be there. That means some blocks can be removed from this particular level and then some blocks from this level can be brought in. So this is called block replacement strategies. Write strategy. What happens on a write? Whenever we are performing a write operation, so what strategies must be used for this write operation? So we are writing back something into memory or into the cache. So how that write operation will be performed, that we must know. So these are the four main questions that are there with us now, that we are going to actually take care. So common memory hierarchy. In a typical computer system, you can see the memory system is managed as two different hierarchies. Cache memory, main memory hierarchy, which consists of 2 to 4 levels and is managed by hardware. We have seen that. The main objective of this particular hierarchy is provide fast average access time, for the instruction and data. The main memory or the secondary memory hierarchy, which consists of 2 levels and is managed by software, that is by the operating system, which is the interface between the user and the hardware part of our computer. So this particular part, that is main memory and the secondary memory hierarchy, which consists of 2 levels, is managed by software. And what is the main objective? Provide large memory space for the user, that is called virtual memory. So basically, this virtual memory is a concept where it says that you have a large memory space at your disposal, but actually you are having the space as main memory only, but programs and data are brought from secondary storage to main memory as and when it is required. So by this means we can actually say that we have a very large memory space available, although we are not having a large memory space, but using such techniques we can have this. So this is called virtual memory concept, so which will not be taken up in this particular course in detail. So this is the typical architecture or typical memory hierarchy of Intel Core i7. So this is core 4 cores, core 0, core 1, core 2 and core 3. So, inside each of the cores what you have registers, you have separate L1 and L1 cache for data and instruction. We have an unified L2 cache. So, this is common to this core. So, all the cores are having this part separately, they are having. Core 3 is also having D cache and I cache and L2 unified cache. And L3 is within this chip, but it is shared by all the cores. It is not that individual core is having L3 cache, rather L3 cache is unified and it is shared by all the cores. And of course, main memory is outside the chip and this is also shared by all the cores. Now, these are some information, that is L1 cache is divided into D cache and I cache, and the access time is roughly 4 cycles and the size is 32 KB. Now, we can have a 8-way set associative cache. We will see in detail, this is a kind of cache memory mapping technique, so which we will be seeing. L2 unified cache is little larger, 256 KB, and we have 8-way set associative thing, and the access time is much more, which is not much more, roughly close to 3 times, that is 11 cycles. And similarly, L3 unified cache, which is not within this core, rather outside, but on a single chip, which is 8 MB, which is pretty large compared to those, and 16-way set associative mapping is performed, and the access is roughly 30 to 40 cycles. The block size is 64 bytes for all caches. Next is core i7 Sandy Bridge. So, this is how it is there. You have 4 cores, every core has its own L1 and L2 caches, and L3 is shared by all the cores and is also on chip. This is the processor graphics, the memory controller that is having. So, this is the typical picture. So, we came to the end of lecture 29, and where we discussed about memory hierarchy in more details, and we have seen that how memory hierarchy actually affects the overall performance. Thank you.